There's an old joke that fusion is the energy technology of 20 years from now, and always will be, and yet that technology may finally be on the horizon. Welcome to Science and Futurism with Isaac Arthur, and I am your aforementioned host, Isaac Arthur, bringing you hopefully accurate glimpses into the future for the last decade, and now with 90% more letter R's, though there are subtitles available on all our episodes. Besides having a stubbornly lingering speech impediment and a science show, I am also a physicist, and one of the things that attracted me to the field was energy production. I grew up in the 1980s when fear of nuclear war was probably at its peak, fossil fuel concerns were beginning to arise, and solar was a distant dream. Global population growth was very fast, and there was always a concern, bordering on dread, that we were going to have a Malthusian catastrophe and all end up living in the burned-out ruins of a deforested, toxic, and irradiated planet. This was all about the time that nuclear fusion was getting its first developmental disappointment phase with the public, as it had started getting talked about as an option that we might have in a couple decades in the 1950s and 60s, and seems still almost entirely theoretical. Add to it, we would soon get inundated with a lot of cold fusion designs, and while some were at least reasonably sincere and sane, many more were utter scams and hoaxes. At the same time, even nowadays where we've got intense and credible fusion research going on, we do tend to get deluged by lots of reports of how this or that device made breakthroughs with achieving net energy gain or getting as much out as in. Today we'll cover the basics of how fusion works, and indeed dip into it deeper than most fusion videos do, then move into discussing some of its practical challenges, economics, the overall environment of the energy sector, how fusion development has come along in the last few years since we last deep dived fusion, and ask about its long-range impact on civilization. Now, odds are good that you already know the basics of fusion if you are watching this, and we did deep dive that more in our episode Fusion Power some years back. But even folks who could tell you that fusion is when we slam atoms together to make bigger atoms generally are missing some key details. One of those is very important for fusion technology. We often tell people who are upset about the slow progress of fusion to be reasonable, as we are trying to replicate the million-degree conditions in the interior of a star inside a small facility, and it is very hard. And indeed it is, but that's not what we're trying to do. You've probably heard that the Sun is mostly hydrogen, 92% of the atoms or 74% of the mass. Virtually all of the rest is helium, and the Sun is about halfway through its lifetime of turning hydrogen into helium. This tends to give people the impression that we started as hydrogen and that helium buildup is the byproduct of fusion in the core. It is not. The Sun is now 74% hydrogen by mass. It began at more like 75%. Almost every atom in this universe is hydrogen and helium that formed within the first 10 or so minutes after the Big Bang, when conditions were vastly more condensed than now, and indeed vastly more condensed and hot than the center of even the biggest stars. Fusion, when it occurs, produces a lot of energy, but it occurs very rarely in our Sun, proportionally speaking. About 600 million tons of hydrogen turns into helium every second, or 596 million tons of helium, with the rest of the mass energy turning into photons and neutrinos. The latter, those neutrinos, are very weakly interacting and fly right through the Sun into deep space, where only a minuscule fraction of them will ever be absorbed between now and the end of eternity. Those photons, all in the powerful gamma-ray range, get reabsorbed by other atoms as heat, and that heat slowly makes its way to the upper layers of the Sun, where superhot gas cools them by emitting the sunlight you and I see, in a process no different than a red-hot piece of metal like those inside old incandescent light bulbs. As huge as 600 megatons a second sounds, it's really quite small compared to the Sun's total mass, as all that fusion is so rare that most hydrogen atoms in the Sun will never end up as helium during the Sun's 10 billion year main sequence lifetime. After that, as it expands into a subgiant and then a red giant, around half that remaining hydrogen mass will blow off into space, along with similar proportions of helium and other elements in the upper layer, in a planetary nebula. which planets do not form from, incidentally. Then it will all collapse into a big white dwarf core that, depending on mass, will be composed of helium, carbon, and oxygen, themselves byproducts of helium fusion. And actually most white dwarfs, known as DA white dwarfs, have an outer layer of hydrogen still too. That's the natural fusion process in stars, and the reality is it's way too slow for us. The Sun's core barely allows any fusion, so that it produces a staggering 3.85 times 10 to the 26 watts, or 385 trillion watts. However, its mass is even more staggering, 1.99 times 10 to the 30 kilograms, meaning its power-to-mass ratio, which you may think of as power-to-weight ratio 2 in this context, is an abysmal 0.1934 milliwatts, meaning a 10 kilowatt reactor, good enough to run a house or two, would come in at 52 million kilograms, or 114 million pounds of fusion fuel in the Sun's core to run that thing, plus any reactor housing and power production. Difference being, it will run for billions of years. Your typical gasoline generator will run somewhere between 10 to 100 watts per kilogram of generator, which is on an order of 100,000 times higher in its power-to-rate ratio, but will go through a gallon of gas fairly quickly, on an order of a gallon or two of gas, or several liters of fuel, per hour. So 52 million kilograms might actually last you several million hours, or several centuries, which is a long time, but nothing compared to several billion years, tens of millions of times longer for the same mass of fuel. Needless to say, we could use a reactor that had that ultra-low power-to-weight ratio, but the problem is you have to maintain that reactor running at millions of degrees for billions of years, and that probably means completely rebuilding it several million times at least. So that efficiency of energy-dense but slow fuel doesn't help you much. This power-to-mass ratio is even worse for most stars, since they are lower mass than our own and slower to burn. A M9 star, for instance, the dimmest and longest-lived of red dwarfs, doesn't put out a fraction of a milliwatt, but a pitiful 7 nanowatts. As a reminder, milli is the prefix for thousands, micro for millions, and nano is the prefix for billions. Our Sun's pitiful power-to-mass ratio is still a few hundred times higher than the weakest of stars. On the other hand, those biggest stars, like an O1 star, amongst the biggest and brightest blue-white giants, has a power-to-mass ratio of 3 watts per kilogram, finally doing decent, at 17,000 times more power-to-mass than our Sun, and more than 400,000 times that cool M9 red dwarf. Now we're getting somewhere, and these stars generally are very short-lived. They generally only live 1 or 2 million years, then explode as a supernova, and are big enough that they can result in a black hole instead of the neutron star most supernovae leave behind. So for a useful fusion reactor, we want to emulate conditions like those in O1 supergiants, not our own yellow dwarf. Fusion rises exponentially with core temperature. Those tiny M-type stars can be as little as 3 million Kelvin to 7 million. K-type orange dwarfs will be 7 to 10 million Kelvin. G-type yellow suns like ours will be 10 to 15 million. F-types 13 to 15 million. A-type 15 to 20 million. B-type 20 to 30 million. And O-type 30 million all the way to 50 million for those bigger O1s. Temperature also will rise as they age, and you can even get a helium flash, which is not hydrogen to helium, but rather helium to carbon. Ignition of helium takes a lot more temperature, that's the 100 to 200 million Kelvin range. During the helium flash though, your power production goes up by a factor of roughly 100 billion, and similarly with a supernova itself. That is a very fast and intense process, even by the standards of short-lived giants. Here we're not in fractions of watts per kilogram, or even watts per kilogram, but hundreds of billions of watts per kilogram, just short of what an atom bomb like Little Boy achieved, while a fusion bomb can do 100 times higher yet, outperforming supernova in power-to-mass ratio. I think that's worth going over because a lot of fusion discussion just handwaves over these scales, and it's a reminder that we do have functioning fusion power, and indeed at a much higher power production rate. You can throttle that by detonating a bomb inside some gas or fluid, much like the inside of a star, and letting that hot gas release energy more slowly as heat. Even during the Cold War, we never really mass-produced hydrogen bombs, most of the cost of which is the missile, but you can get a cost per kilowatt hour of hydrogen bombs of about 1/10 of a cent, even if we're including the ICBM, rather than 10 cents a kilowatt hour. And this is why in a lot of our fusion videos, I will point out that we absolutely already have nuclear fusion and could economically employ that. The cost is higher for fission bombs but still quite low, but would require way less infrastructure. You essentially need a reactor big enough that when you detonate that bomb, it can absorb the whole blast, and do it repeatedly, which is implying you've dug out some crater kilometers wide and lined it with concrete and watertight liners and domed it over, and put big steam turbines in chimneys coming off it, and dropping bombs into it to detonate and heat that water to a boil. Needless to say, that's exactly the sort of mega project I love, and you could power the whole US by detonating a megaton device every hour or two. But that would imply you only have a handful of such facilities on a given continent, and works way better if you have superconductors or a power grid built around ultra-long distance transmission. There's no magic engineering involved either, it's just a heavy lift to build that, and you probably end up having all your major industries flock to be near it, given the advantage of proximity for limiting power transmission loss. So you might end up with industrial megacities surrounding at most 100 or so mega reactors worldwide. Not the path we want to go, I think, but it's my rebuttal when folks say fusion can't work, and why I'm so casually optimistic about our long-term power sustainability. The challenge for fusion, though, is to try to make it somewhere in or above that O-type star temperature and keep it there. On the other hand, it is much easier to cram deuterium together with itself or with tritium than it is to cram regular hydrogen together or helium. When it comes to nuclei for nuclear reactions, hydrogen is just one proton, deuterium a proton and neutron, tritium is a proton and two neutrons, helium is two protons and a neutron, and helium-4, regular helium, is two protons and two neutrons, also called an alpha particle, from where we get the term alpha radiation. Beta, incidentally, is electrons and their antiparticle the positron. And gamma radiation is photons of light, including ultra-powerful invisible ones and weak radio waves and microwaves. When protons whack together at high speed, they have a barrier to actually hitting due to their mutual positive electric charge, which repels. And this Coulomb barrier is higher than for deuterium or tritium because they have the same charge but more mass or momentum from that neutron, like a truck instead of a car. Even at the same speed, it takes a stronger wall to stop one. So when the other atom is shoving back against it electrically, it just has more inertia to continue with, thus they can hit at lower temperatures. Once they actually collide, if they do, most of the time a proton-proton collision results in a diproton, a temporary particle of two protons. They last for a few trillionths of a second, which in the context of particles moving thousands of kilometers a second and interacting in a range of less than a trillionth of a meter makes them about as united and stable as two people giving each other a high five while passing by. They're not married. They then separate into two protons again. Mission failed. And that's even when they succeed in the hand clap. Most times they miss each other by several metaphorical feet. During that brief moment of union, they can undergo beta decay. It's sort of like your odds of getting hit by lightning while giving a high five, and of similar odds, but every so often that beta decay occurs, about one time in 10 billion diproton meetings, and we get left with not a pair of protons, 4 up quarks and 2 down quarks, but instead a proton and a neutron, or 3 up quarks and 3 down. And that is a proton and neutron. In fact, those are only the valence quarks, akin to the valence electrons that make up the outer shells of electrons around an atom. There are a lot more C quarks involved, See our Antimatter Factories episode for a deep dive on what's going on down there at the hazy edge of reality. This decay also spits out a positron, the electron's evil twin, and when it finds an electron, being of opposite charge, they'll capture and orbit briefly as positronium, spinning down into each other and on collision emitting a pair of gamma rays of 511 keV each, which will then be absorbed as heat by other particles, warming that star or fusion reactor. Each of those gamma rays has about 200,000 times more energy than the photons you and I normally see by. A neutrino is also released when that positron gets kicked out, but it will fly off to eternity, except in the most extremely dense fusion events, like actual supernova or neutron star mergers, where we get large numbers of neutrinos absorbed and useful elements like phosphorus produced. How often collisions happen is based on density and temperature. The hotter you are, the faster a particle inside you is moving, so the more collisions it gets in, and the denser the medium, the more often it's running into stuff. This is why hot gases spread out, but these are held together by mass. In a fusion reactor, we are usually substituting in magnetic fields for mass. The more collisions, the more likely a di-proton meeting will occur in any given moment and time, and the faster the collision, the more likely they'll actually meet to be a di-proton rather than deflecting to the side from their electric charge. This is generally why we don't talk about using pure hydrogen in fusion reactions. Deuterium is plentiful, and regular hydrogen is harder to get across the Coulomb barrier and need 10 billion whacks to get it right. So not really a priority as long as we've got deuterium and there's no shortage of it. If we had some magic technology, what we call Clark Tech on the show, that made those diprotons more likely to decay as deuterium, this would change that or even be a pathway to cold fusion, or at least very warm fusion. So too, bigger particles like helium, or even bigger ones like carbon or oxygen or nitrogen, move slower at higher temperatures, so they collide less often and have less inertia to override their own Coulomb barrier, keeping them from fusing to another positively charged nuclei, hence why fusion is mostly hydrogen and very rare. Deuterium can combine with deuterium or tritium much more easily, and while tritium only lasts for around a dozen years on average, deuterium is stable and most deuterium dates back to the Big Bang itself. Stars do produce a lot themselves, but they also burn through it quickly as it fuses more easily than plain hydrogen. Helium-3 is less common than deuterium, and it is also stable and mostly dates back to the first few minutes after the Big Bang too. It is frequently created by a deuterium atom colliding with another proton, and this also releases a good amount of energy, indeed around 5 times as much as that positron released when it was formed in the creation of the deuterium and collided with an electron, destroying both. This is a much more common reaction than creation of deuterium by proton collision, so deuterium doesn't last long in stellar cores, or in any star that's convective, which is to say, boils and bubbles its contents around from its core to its surface. This gets rid of the 20 to 30 parts per million of deuterium a star would be when it formed, as that's the general prevalence of deuterium since the Big Bang era. Tritium, with its 2 neutrons and only 1 proton, has an even shorter lifespan in stars, since not only does it fuse easier, but it has a 12-year half-life to turn into helium-3 as well. Now that helium-3 is sitting around in the core, you're probably thinking it just needs 1 more neutron, and you are right, but those aren't lying around. Free neutrons decay even faster than tritium, more like a dozen minutes than a dozen years. Helium-3 will not work well with a lone proton, as that's now 3 protons and only 1 neutron trying to merge, at lower speeds than normal for a diproton meetup. So fusion here is actually 2 helium particles ramming into each other. This knocks a proton off each and gives you a helium atom and 2 lonely protons again, waiting for their chance to ram headfirst into another proton 10 billion more times till they make deuterium. This also releases about a dozen times the energy our positron-electron merger from the deuterium reaction released. No neutrinos are formed in this step or the deuterium to helium-3 step. They generally come from beta decay. Many other reactions can occur, especially at higher temperatures, but that's our baseline right now. If you followed all of that, you now know more about fusion than anyone who isn't a physicist or serious fusion enthusiast knows. Indeed, most physicists who aren't either in nuclear or astrophysics will generally not recall that, or know much beyond that. It's not exactly the brief intro to the topic I planned, but I feel like a lot of fusion videos really skim over the details. Now, if you followed all that, you can guess how we make fusion happen in a lab, or a bomb. We attempt to replicate extreme conditions, and that can be by using a big linear accelerator to run charged particles into other charged particles, or the circular variety. We can produce energies far beyond what a star has inside it, and indeed these days replicate conditions not inside an H-bomb or a supernova, but actually during the first trillionth of a second after the Big Bang, on the boundary between the electroweak epoch and the quark epoch. That itself would last the hadron epoch beginning a microsecond after the Big Bang, before we started getting hydrogen and helium a minute later. You might wonder about calling those epochs, considering how short they were, but more events happened during them than has happened since, in 13.8 billion years. Colliders and accelerators are the easiest way to get super high rates of fusion, but it really cannot be sustained by itself, just because you're dumping so much energy into all those magnets trying to speed up a minuscule fraction of a gram of matter. So it's good for scientific study, but not for a fusion reactor. This is one of those examples of where we hear talk about making it to the necessary level of energy. If I spend 1,000,000 joules of energy to accelerate some particles, and a handful of them collide and fuse and release 500,000 joules, I don't get a net positive energy out of that. For a long time, that was what we were aiming for, where the kinetic energy of all particles was less than the energy released when those hit and released more energy. But then we moved the bar, because often to dump 1,000,000 joules of kinetic energy into a bunch of particles, you need to spend 10 million, or even more. Once you get to that break-even point, you now need to factor in how much energy you need to spend to build and maintain that entire structure, which will be an even higher break-even. And now you've produced a bunch of energy, but how much did you succeed in converting to electricity? Even if you got it all, 50% converted into electricity instead of lost to heat would be pretty good. Now it's in the power grid and much is lost to transmission. Each of those are different break-even points, and we still haven't gotten to the point of being able to produce electricity at an economically competitive cost and scale. But they all are worthy goalposts deserving praise. It just tends to make it sound to the lay public like we spiked the football on the goal, then spiked it to get on the same goal the next year. Especially as we do have several different projects approaching it from different methods, all claiming results, and often getting hyped up for almost obtaining the goal. Then again when they got there, then again when they comfortably exceeded that goal, 90% of break-even, then 100%, then 110%. But a linear collider isn't going to get you there because the particles are very tiny and the distance to the target very big, so not many collisions happen. They miss the target. Ring-shaped ones often have the particles going around over and over, so they get multiple chances at collision with the stationary target near the detector. The tokamak actually looks like a collider in that it's a big donut shape, though a thick one rather than a big skinny ring, and tends to be our default design, as it's generating a powerful magnetic field to try to keep all those charged particles inside and slamming together. This replaces the immense gravity keeping those particles together inside a stellar core. This doesn't keep neutrinos in, they will generally pass through anything that's not a neutron star, but it also doesn't keep neutrons in, and they do a lot of damage when they hit equipment. So you need shielding beyond this, able to absorb them, and able to absorb the gamma rays released, as well as the photons emitted by hot gas. Now when we talk about breakthroughs with tokamaks, here we don't see as much on break-even, and more about temperature and period sustained. The one that caused me to create the poll that the audience selected this episode from was from back in February 2024, was the K-Star reactor's newest success. And yes, there was often a long lead-up time on episodes here like that, though sometimes I've made them the same day they aired too. Fusion reactor progress tends to be even slower, as it can take a decade to get the funding to build a device, then a decade to get it built and operational, and another decade of tweaking while we take that research and figure out new options and hunt for new funding. K-Star started back in 1995 and took over a decade to get construction started. During that time, which is also while I was doing college from 1996 to 2003, undergrad and graduate school, we did have some early tokamaks going. The ones I remember best are Doublet 3 from General Atomics and is still going, the follow-up on Doublet 1 and 2. We also had JET, the Joint European Taurus, from 1983, and JT-60, or Japan Taurus 60, now JT-60SA, the largest operational superconducting tokamak. And again, all tokamaks use a donut-shaped magnetically confined torus of superhot plasma. And there were also non-tokamak designs, some rather novel. Again, see our Fusion Power episode, which dives into some of those, but many are strictly for better knowledge of particle physics, not for power generation designs. For others, we do have a spherical tokamak design, like NSTX, but it's been in limbo for almost a decade now, working on a colloidal coil problem. The polywell design went public about the same time the channel started and reignited my own general interest in fusion, but hasn't made much progress of late, that I've heard of anyway. Same for Z-Pinch, though I'm more optimistic there and for inertial fusion energy in general, and this is the approach that involves zapping pellets of fusion fuel, often with a laser, with the intent of delivering all that energy very quick to compress the pellet and superheat for quick fast fusion. I always think of it as a micro-nuke, though it's a debatable analogy. We also have the Stellardrone design that Lyman Spitzer came up with back in the 1950s at Princeton, another of our early fusion ideas, along with magnetic mirrors and Z-Pinch, and another personal favorite. Well-known ones you'll see in the news are Wendelstein 7X in Germany, HSX in the US, the helically symmetric experiment, and the LHG, or Large Helical Device, in Japan. By and large, these are internationally cooperative efforts too. Nobody's hoarding info that I've heard of. Folks will sometimes say they're developing something and keeping it secret for patent reasons, but in my experience, that's usually the sign of a scam. I'm happy to discuss any of these in their own episodes if folks like, but we're already long for today, and I feel like we should explain at least one of these reactors and what the holdup is. I tend to feel that tokamak remains the leader of the field for producing possible power, and again, K-Star holds the best record at the moment, at least when I wrote this episode in August. They think they'll raise their time by almost a whole order of magnitude in the next few years too. K-Star is short for the Korea Superconducting Tokamak Advanced Research Reactor, which broke its own previous record of 31 seconds to sustain 100 million Kelvin, or 180 million Fahrenheit, for 48 seconds. This is not quite as awesome as it sounds, as first, it's hot but not dense. Many collisions are happening at the right speeds, those inside big bright supergiant stars, but the density in the tokamak is less than that of air, even thin air, so you aren't getting very many collisions per second compared to a similar volume or mass of a stellar core. They've been tweaking and improving it for years. I've looked over their timeline on Wikipedia, and just about every year they had a new change that resulted in a new higher temperature or longer period at that temperature, and they've generally got a headline for each. As have other projects, and they all deserve it, but their overhyping by some of the popular science press tends to feel like it's dangling progress at readers. This is not going to be a quick area of research. You might be wondering where those neutrons are coming from, since proton-proton collisions do not emit them, and deuterium-proton don't, and helium-3 to helium-3 doesn't either, just two protons there. But often we're contemplating deuterium-deuterium fusion, as it's plentiful and fuses easily to itself, and half the time that results in a tritium atom and a proton, and the other half the time helium-3 and a neutron. This is why helium-3 fusion is often called aneutronic, and is very tempting for fusion, because while it needs higher temperatures to happen, it isn't releasing neutrons. Deuterium-deuterium and deuterium-tritium, which are both much easier to produce, do produce a lot of neutrons, half the time for deuterium-deuterium or DD fusion, and all the time for deuterium-tritium. But we really like deuterium-tritium because it has the lowest Coulomb barrier and thus can be done fast and easily at lower temperatures. Plus it releases about 5 times more energy than the average deuterium-deuterium fusion, and spawns tons of damaging neutrons, which again is rough on equipment. Tritium is also rare and runs about $30 million a kilogram, and at that cost, Even if we got everything else involved for free, no construction or maintenance or power lines would still run over $1 a kilowatt hour. The easiest way to make the stuff is by breaking lithium into it in a breeder reactor, and virtually all the lithium in existence was made in the Big Bang and not much of it, so I generally do not consider tritium-based fusion to be a long-term power supply, just handy for initial efforts, research, and special applications. If we get other fusion working, we will be able to produce more tritium, and lithium for that matter. They do get made in stars, but just don't last long, so never see the outside of them. Such being the case, we could be running a fusion reactor that was producing them and just vent gas out, then centrifuge on cooling, or even possibly magnetically separate them, but it would always be a niche use, much as radioisotope thermal generators are compared to fission reactors. So it's really deuterium-deuterium fusion that we are interested in, because there is a vast abundance of it here on Earth. Alternatively, helium-3 is far less common and only even modestly abundant in the outer gas giants. The supply of it on the moon is rather overhyped. If you've got a good working fusion economy, then you can economically transport that material back from deep space, as an example of impacts of fusion, but don't assume you are pulling off non-stop acceleration with a fusion reactor in your spaceship like in The Expanse. What you are achieving is a power source able to move ships much faster than the speeds planets tend to orbit at, and to let you set up shop on planets far from the Sun with an abundant power supply. In truth, at the interplanetary scale, it doesn't offer much for space travel and development that regular nuclear fission designs don't already offer, with the caveat that deuterium in the solar system is a few orders of magnitude more abundant than fission fuel, and regular hydrogen even more abundant. Its longer-term use is for large settlements and planetary empires, along with interstellar colonization, where fusion gets very handy. In many cases, big solar panels or mirrors will work better in space too, closer to the Sun, so don't assume fusion automatically means every other power source disappears. A reactor, especially one spitting out neutrons, is going to be an expensive object to build and maintain, and I tend to think of them as best on a planet with a lot of water or ice available for cooling, bigger spaceships, and work far from the Sun. Otherwise, you need a big radiating infrastructure to cool the device off, and for instance, a fusion reactor in space near Mercury would probably be quite pointless compared to a solar collector. Your equipment can only handle getting so hot before it melts, after all. It is worth noting that the big advantage to fusion is that it runs on a virtually inexhaustible and abundant fuel, so you are paying for construction and maintenance, not fuel. Solar, wind, and hydroelectric are the same, 0% fuel, whereas oil plants tend to run at about 70 to 80% fuel cost, natural gas about the same, coal a bit less at 60 to 70% fuel cost, and nuclear way down at 20 to 25%. Needless to say, you can see why many of us like nuclear. There is also the reality that all those renewables would probably get lower construction and maintenance costs if they were being produced and used to the same degree coal and oil are, but the reality at the moment is that coal and oil are just very easy to work with to build and maintain. It's also a reminder that a lot of the cost isn't power production at all, but the distribution of that power between the power plant and your wall socket. That comes in two parts: the delivery of high voltage to substations, which makes up somewhere between 10 to 20% of the cost, and then from the substation to the consumer at more like 15 to 25%. This varies a lot by the community served, the energy source, changing fuel cost, and even time of year, but around a third is a good value to recall, as a loose rule of thumb. Now, combustion engines are just easy to build and maintain, so we probably want to keep in mind that there are renewable options out there for them, like burning wood, agricultural leftovers, biofuels, or even something like dried out algae. They are solar powered. They are nowhere near the efficiency of a modern photovoltaic panel, but you don't really have to build and maintain them. We don't know how much a fusion reactor will cost to maintain. We tend to figure they are less brutal on the reactor than nuclear fission is, but that's about the only reference point we have, and even that is speculative. Hydro, wind, and geothermal are fairly location dependent, but their improving technology could widen their location. So it's mostly solar versus nuclear for the future, though solar is fusion powered, of course. The question comes down to asking if the total cost of a megawatt of solar production is less than a megawatt of fusion reactor, with the notes that we expect fusion to do better when bigger, meaning longer transmission distances to homes, and solar does better in good sunny weather, meaning it needs power supplementation by other systems or inexpensive to build and maintain power storage options like batteries or molten salt. Nor is it simply a space issue, as solar and wind both use up large locations compared to equal power plants, which can be why space-based solar power gets attractive, as it doesn't use up good, well-lit farmland. Space, handily, has a vast abundance of empty space. To minimize power transfer losses, you want generation close to cities, and that's valuable real estate, either raising production costs or raising housing costs by removing it from play. This is where superconductors can be great, since they let you put your solar all in the Sahara Desert or floating on the deep sea, where their undersides might actually help trap nutrients so the well-lit spots can actually have plant and algae growth of their own. Most biomass is on land, and what isn't is mostly on lakes and coasts, but most of Earth is deep ocean, and generally there's more than 1,000 times more biomass in a given area of land than an equal area of deep sea, simply because light is plentiful but nutrient near the surface where it can get sunlight is not. You could probably run a lot of biofuel production off algae in the sea on floating solar panel tanks, but you could be using that solar power to grab carbon dioxide out of the air and hydrogen out of the water and make it into carbon-neutral hydrocarbons for burning. This is not energy neutral, but hydrocarbon generation is a good way to take excess peak power and store it for off hours of darkness or low wind, as well as to use in vehicles where hydrocarbons are inherently more efficient than modern batteries in terms of energy density, joules per kilogram. Batteries do work decently for cars, for instance, but really don't have the power density for aircraft, let alone spacecraft. So even a good solar and battery economy, you still want some carbon-neutral and renewable source of hydrocarbons or other chemical fuels that are energy dense, like straight hydrogen. Also, those traditional electrical plants do take space and indeed have to actively cool themselves by water, which is a great way of desalinating seawater to get fresh water, but does also mean they're often on valuable real estate near coasts or rivers themselves. That was hardly an exhaustive list of alternate power options, and all are very subject to massive shifts in viability based on changing technology. We'll explore them more in our Off the Grid episode next month. Someone might invent a battery tomorrow that could store electrical energy more densely than chemical fuels and leak energy slower than 1% a month, and suddenly nobody wants gas-powered anything. Microwave power beaming also gets around a lot of this, since it can send energy from anywhere, even over millions of miles through space, with losses of 10 to 20% into heat on reconversion to electricity when absorbed at the receiver. Someone might make an awesome, cheap-to-mass-produce home tank for growing algae and a washing machine-sized extractor and converter that lets you produce some carbon-neutral gasoline at home. Then everybody says no to big lawns and yes to big algae vats in their backyard or on their roof even. There are so many options, and it's why it's easy for me to be a techno-optimist. Nobody, and I mean nobody, actually knows how the costs on all these will shift over the next decade of improved automation, let alone 20 or 50 years down the road, and especially for fusion since we don't have a working model. This is why, while fusion is very desired as a technology, it's also not considered the golden goose or holy grail it sometimes gets portrayed as. For me and others, it tends to be that vital technology for ensuring we have a steady and unlimited power supply in a century or so when we are worried of running low on cheap fission fuel and do not want a lot of land space or low orbital space taken up by solar panels. It also unlocks the gateway to practical deep space colonization and interstellar travel. Even if it takes us a few more centuries to get fusion, it's well worth it. Our supplies of uranium and thorium will last a very long time. We have at least several centuries of uranium before we even need to switch to breeder reactors. And our numbers aren't really growing that fast these days, while our farming technology is, so we aren't in imminent peril of running out of land or sea for solar and parallel renewables. And if commercially viable fusion was invented tomorrow, it would still take a couple decades to get it deployed globally, so it wouldn't be an immediate fix for ecological issues involving fossil fuels. Does this mean we are not interested in getting fusion working? No, of course not. As I often note, new energy technology tends to involve a lot of circular firing squads from folks who have their favorite energy tech and take shots at the perceived flaws of the others. I loathe that sort of behavior and strongly encourage heavy funding of all energy R&D, even fossil fuels, precisely because we don't have a crystal ball to the future of energy. An improvement in how we use coal or oil could have great ecological effects, but some would oppose it on the rationale that it might make solar or wind or nuclear less attractive or decrease the urgency of dealing with the problems of fossil fuels. Which might indeed be true, but by default, I assume that the more technology and prosperity we have, the better we can solve all problems. I won't soapbox on the matter, but in years of doing this show, I talked to folks from every area of energy research and development, and almost without exception, anyone advocating for it will pause while discussing the upsides of their preferred system to throw shade on the others, often even inside the same niche too. I understand why, I just find it very irritating, and many go beyond raising the real pros and cons to cherry-picking the data. Fusion tends to get waved aside. After all, it doesn't even have a working model yet, and honestly it doesn't belong in our current considerations of energy tech. Our current civilization tends to rebuild everything on 10 to 40 year timelines, so we don't really benefit a lot by waiting for new technology as opposed to deploying what's already right here. And right now, fossil fuel is still the overwhelming leader if we ignore its scarcity and ecological issues, and then it goes to nuclear and solar in my mind, with both being competitive if we choose to commit to doing them, so I favor doing both and seeing which comes out best after a couple decades of usage. But let's remember that nuclear fission is the only fast power tech we've had. We took centuries to develop coal and oil or chemical fuel-powered heat engines. Solar is just starting to become economically viable in its own right, and it's almost 150 years old. Wind is even older, so is geothermal and hydro. So the whole 20 years thing is just an over-memed leftover from our early successes getting fission working, and how quick we got fusion bombs after getting fission bombs. Folks jumped the gun, and fusion would be a fast racehorse of development if it was commercially viable by 2104, and yet it could be here by 2044 or 2054. Things move faster once it gets clear there's a pathway to develop we can pump money and people into. Now, why does it matter? Better automation and AI is going to make our power grid cheaper and easier to maintain, at least proportional to the overall economy as time goes by. Same for hardware-heavy energy sources compared to fuel-based ones, like most renewables. But if we can get deuterium or helium-3 fusion going, it now means an unlimited fuel supply that works day and night and in bad weather too. It's also compact and movable, unlike a giant solar panel field using up real estate or a hydroelectric dam, and even orbital solar has some constraints for clogging orbital space or being a large and soft target vulnerable to attack. You can't really bury these things inside bunkers the way you can a big reactor. It lets us do awesome things like suck carbon dioxide right out of the sea and sky and turn it back into fuel for vehicles, and power vast vertical farms made of energy-intensive substances like aluminum and glass to feed a far larger population on a far lower budget of space, resources, and ecological impact. There is no end to the benefits of cheap power, especially one that has a near infinite fuel supply and requires no conversion of land and growing space to fuel it. It's what can run the active support for the immense orbital infrastructure we like on this show, such as orbital rings and space towers. It lets you build enormous lighting arrays in the oceans deep beneath Europa near Jupiter to terraform that moon, or power vast orbital habitats deep in the Kuiper Belt, sending comets onto Mars to give it oceans, or warming asteroid mines in their habitats deep in the asteroid belt. It lets us send out spaceships to other star systems that won't need 1,000 years to arrive. In this regard, fusion, the power that drives stars, is also the power supply that would take us to the stars. We were talking about how fusion might help us power and even feed future civilizations, including those on distant planets someday, And there's actually a question whether or not you would find it easier to build domed farms on planets like Mars or Venus, or just pipe down food on ships or space elevators from orbital farms. Whether or not you're feeding planets with them, you also have a large space-based population needing to eat, and you probably aren't dedicating space in your over-engineered and beautifully landscaped space habitats to that either. In this month's Nebula exclusive, we'll be examining those orbital farms. If you didn't know, Nebula, the largest creator-owned streaming service, has tons of extra content from myself and many other creators, including a new, full-length episode of SFIA like Orbital Farms that we release on the first day of every month. And every episode of this show also airs on Nebula a few days early and ad-free, no random commercials or built-in ads like this one. Using my code, IsaacArthur, you can get 40% off and join for about $3 a month, about the price of the drink or snack you've been enjoying during the episode. We also now have lifetime memberships and gift cards available to let you share Nebula with friends and family. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code, IsaacArthur, you not only get access to all the great stuff Nebula offers, like Orbital Farms, you'll also be directly supporting this show. Coming up this Thursday, November 14th, we'll take a detailed look at the question of what we should do if aliens made contact with us, and it turned out the Fermi paradox wasn't a paradox after all. Then we'll ask if gravity itself might be the main cause of the Fermi paradox, before asking how ultra-relativistic spaceships might be built and function under known science. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching and have a great week.